Hi everyone, this is a video introduction of the Riemann sum of a function. Before the time of Riemann, the definition of the area of a region wasn't really carefully thought out. It was something intuitive to everyone, and I guess they only paid attention to how to compute those areas. But it's a Riemann who are concerned with this part of the foundation in mathematics and try to give a proper definition of the area of a region. So I have prepared this animation. The function we're considering here is e to the negative x squared, and the interval we're considering is -1 to 2. So here we considered 5 intervals, so we divide this -1 to 2 into 5 equal pieces and erect a certain size of rectangle. And the rule of choosing the height of this rectangle is the following. For this example, we looked at the first interval and chose a midpoint. At that midpoint, you go up directly above until you see the point on the graph of y equals f of x. Sometimes the function hits the negative axis of y. In that case, we have to look down and to find a point on the graph of function. So for that first interval, we look at this midpoint, find this point, and choose that as a height of this first rectangle. Let's take a look at the third one in here. This is third interval, and that's a midpoint. And look up, and there's a point, and choose that as a height of this rectangle. So you repeat that 3 more times with other intervals. Here we create this set of integrals. This midpoint, I think, has some advantage. Of course, the shape of the function is different, and this midpoint will lose, but overall, those examples we see this in classroom, midpoint has a following advantage, I think. For example, if you look at the third rectangles in here, this rectangle is not quite the same as the shape determined under this actual curve e to the negative x squared. But this one here is a rectangle is overestimating, and over here the rectangle is underestimating. But if you compare the area of these two regions, the shape of this two region, even though this curvy part and that curvy part is slightly different, I think they are quite similar to each other. So by looking at the shape, before we even define the area of the region, just thinking about this intuitive notion, the area of this rectangle is measuring pretty good area. Is measuring the area of this region bounded under this curve pretty nicely. And the same thing is happening in here and there, if that part. Only part is not really doing a good job in terms of how close is this rectangle area compared to the region under the curve. I think is the middle one in here, but other things are pretty good. So what we are calculating underneath in here, Riemann sum, is the area of these 5 rectangles. Here it is saying that it's 1.6411, and if you just continue this process with more rectangles, and for example sticking to these midpoints for all these different type of partitions, so-called, and that number is approaching to 1.6289, and in terms of first decimal places we got that correct. And below I'm also showing you the more data. These xk's are the coordinates of the right endpoint. This is the first interval, so this is x subscript 1, and that coordinate right there is supposed to be -0.4. That's the coordinate there. If you look at the second interval, the right endpoint is x subscript 2, that's x sub 0, and x1, that's x2, that's a 0.2, and so on. Below here, we are computing the length of each interval, so that's the first interval here. The length between this of this interval is 0.6, as you can see, and as this picture indicates, that length of interval is all the same. If you divide interval in this fashion such that the length of all the interval is equal to each other, we call that regular partition. So interval is divided into equal pieces. Here the length is 0.6. xk star is a midpoint of each of the interval. For example, if you look at the third interval, the midpoint down here, it is saying that it is 0.5. If you look at over here in the fourth interval, is 1.1. So we use this midpoint, like we mentioned before, midpoint to determine the height of the rectangle. What is down there is a delta AK is the area of each of the rectangles. The first area of this first rectangle turns out to be using this height, 0.36. The last one is 0.033 and so on. So if you add them all up, these 5 numbers, you get 1.6411. Let me go back in here and think about other choices of these height points, so-called. Here it's 0.5, that means it's exactly the midpoint. But if we change that choice of these height points, so-called, we leave these 5 intervals, but think about choosing different height points. For example, if I go toward a little bit to the right, we're not using the midpoint, but we're using point slightly to the right side. Maybe it's 2/3 of from the left side in here, and that'll of course change the Riemann sum. As you can see, the Riemann sum is 5.9311, like that. Riemann's idea is not about Riemann's main idea is not about just estimating. It is about properly defining the area of a region. So he had to consider all sort of different type of choice of this height point in there. Here is all kind of same relative location, but he had to free up. Even for this one, we're going to choose this height point. Even for the second interval, maybe we'll decide to choose a midpoint, and so on. So the choice of a height point for even for each of the interval, and even this partition itself, it doesn't have to be this equal length, so-called regular partition. So Riemann's main idea is about, for all possibilities, all different varieties, partitioning this x-axis and choosing different height points even for each of the interval in this particular setting. Out of all these possibilities, he required all those possibilities converge to the same number, and that was the property he required for the area of a region to be properly defined. In practice, it does not do much, but the main reason of we're spending time on listening to me and thinking about this one is to understand the very property that Riemann required for the definition of a region to be properly defined. If you understand that part of the purpose of the Riemann, you will find the content of this video is meaningful to you. Again, it's not about computing the area, it is about the thinking about the concept, whether it's a good concept or not. So, but in terms of comparing these two things, I find the following is interesting. As you change this location of this height point for each of the interval, not changing the number of intervals there, so you can see these numbers varies. And this following is called intermediate value theorem. You can easily think about this one continuously changing. Then as you go all the way to the right, if you pay attention to that one, is too low. As you can see, is 1.49 is far away from 1.62. But if you go all the way to the left side, it is overestimating it to the left side. So by intermediate value theorem, if there must be some value in between that precisely equals these and the number we're staring at there. So there must exist this proper ratio such that this Riemann sum is precisely equal to the definite integral. That's not the purpose of considering this midpoint, but with this animation, that idea, slightly more complicated context of the intermediate value theorem, it's easier to understand with this slide manipulator from Mathematica. Let's consider a bit more of the rectangles put around there. So all the way to here, I think we're looking at the 20 integrals. So if you put around the 20 integrals using that, we're getting quite close to that. If you just use a midpoint, which is 0.5, exactly the midpoint, it's still pretty close. And as you change the location of this height point for each of this interval, this will slightly change the values. And again, the main point of this video is to understand the property that Riemann required for this mathematical definition of the area of a region is properly defined. Thank you.